I'm Daniel Taylor. Every time you learn something, a complex process is occurring. Information is perceived by your sensory receptors, travels along your nerves to your central nervous system, and ends there. Now, by themselves, these mini sensations are not terribly useful. Imagine if you were to receive millions of emails, each one containing just a single letter. Without some organizational method, you would not be able to understand what the emails meant. So it is with our brain. All these sensations are entering the brain from all over the body at every moment. Without some way to organize them, we cannot understand what they mean. The brain has sensory cortices that receive and begin to organize the perceptions that bombard them. There is a sensory cortex for hearing, vision, smell, and muscle feedback information. Touch, temperature, pain, and pressure all go to the same sensory cortex. After this receipt and initial organization, all the information comes together into areas of the brain called associational cortices, where the overall perception of the environment is created. Certain parts of our brain, like the pulvinar, help us decide what to attend to out of the entire perceptual stage and what to ignore. An associational cortex in the frontal lobe evaluates and reasons over the attended perceptions. This is the information that is said to be in the working memory, the information that we have at hand that is being attended to. The number of items we are attending to is our cognitive load, and items include perceptions of the world around us, as well as the reasoning processes that we perform to understand them. Connecting all these portions of the brain are a large but finite number of neurons, which can carry only a certain number of signals at once. Thus, the amount of information that can be received and processed by a particular part of the brain, like the frontal lobe for example, is limited over a given time. This is the cognitive limit, and is based on the neuroanatomy of the brain. In order to effectively understand an experience or concept, the cognitive load of that experience or concept must be less than the cognitive limit of the working memory, or else important details will be lost. In instructional design, cognitive load theory is a method of increasing efficiency and ease of learning by developing instruction that creates a cognitive load that is less than the cognitive limit. To do this, we should look a little closer at cognitive load, as there are three types that are useful in instructional design. Intrinsic cognitive load is contained within the information that should be learned. An example is the number of concepts in the math problem 1 plus 1 equals what? Everyone who sees this problem will have to understand what 1 plus equals and the question mark means. This is intrinsic cognitive load to the problem and cannot be reduced by instructional design. Extraneous cognitive load is that which is added to the information by the designer. It is based on design choices and can therefore be reduced. For example, say we took our original problem and rewrote it as a word problem with flowery language, a few unimportant details, some pictures, maybe a little background music.
It's the final countdown.
The problem is still the same, but now the learner must attend to a lot of extra material that only exists in the design. A novice in the field of mathematics might find this extra material so distracting that he would be unable to answer the question in this form, while he might be able to answer the original, simpler form. Cognitive load theory understands this phenomenon as caused by design choices that have increased the extraneous cognitive load to the point where it, along with the intrinsic load and the problem-solving activity itself, is greater than the cognitive limit. This would prevent the learner from getting the right answer. Now, surely most of us watching this video were able to answer even the extraneously complicated form of the question. This is because we are experts by now in basic addition, due to the development of an accurate addition schema. Based on our elementary school studies in addition, and years of using addition in daily life, we have developed a robust understanding of the concept of addition in our long-term memories. We have added 1 and 1 so many times that the answer is already in our schema. We don't have to do the calculation. We just know the answer. This reduces our overall cognitive load to nil. The fact is memorized. Another element of cognitive load theory and instructional design is to create instruction that encourages the development of such schema. The effort it takes to create problem-solving schema is the germane cognitive load. In general, since the development of useful schema is such a desired end, instructional designers will seek to increase the germane cognitive load while decreasing the extraneous simultaneously. Mere repetition does not necessarily form a schema in complex problems because the cognitive limit is filled by the intrinsic cognitive load of the problem. Thus, techniques are implemented that encourage the learner to think about the process of solving a problem rather than the problem itself. By breaking the complex problem-solving technique down into its component parts, each part can be mastered before moving on to the next, capping off with a lesson that takes the parts, now familiar and low cognitive load, and puts them together. This builds a complex problem-solving schema from scratch that can be used to solve complex problems that were previously insoluble. So, cognitive load theory is an attempt to understand how the brain learns, so that we can create instruction that corresponds. Best practices include reducing extraneous cognitive load by making the presentation as simple and streamlined as possible, and increasing germane cognitive load to develop sophisticated schema.